Hello children, how are you all? As the exams are coming near, I hope all of you have started studying. Today we are going to understand the concept of Theorem 10.2 based on Chapter 10 Triangles, followed by Exercise 10.2 with some questions. In Exercise 10.2, there are few questions as homework. Kindly do it. So let us begin with the theorem as well as the exercise. Welcome class. Today we're going to do another topic, that is number of tangents from a point on a circle, followed by theorem 10.2, followed by exercise 10.2. Now, before we start with theorem 10.2, let us understand one activity that is given in the book. It's written over here in the book. Draw a circle on a paper. Take a point P inside it. So we are taking a circle and we are taking a point P which is inside the circle. Can you draw a tangent to the circle through this point? Let us see if we can draw it or not. If I were to pass lines from here, suppose I want to draw the tangent either from here or say another line passing through this particular point here, or any other line passing through this particular point over here. What do we find? We find that all the lines through this point intersects the circle in 2 points. If I talk about this particular line, it is intersecting here. If I talk about this particular line, it is intersecting the points here. If I am talking about this particular line, it is intersecting the circle at these two distinct points. So it is not possible to draw a circle, to draw any tangent to a circle through a point inside it. So tangent is not possible in this case. Let us see another case. They are saying again to draw a circle, and this time we have to take a point P on the circle, that means on the circumference. So this is the point that we have taken on the circumference, and they are asking us whether we are able to draw a tangent or not. Of course, if there's a point on the circumference, we will be able to draw a tangent through that point. That is there, point P on the circle. Now, third case, they want us that if there is a point P which is outside the circle, will we be able to draw the tangents? Suppose this is a circle, and P is a point outside the circle. Will we be able to draw tangents from here or to the circle? Yes, of course. To P, we will be able to draw lines that will be on the circle. One point exactly touching on the circle. Here we can see that in the third case, we can draw exactly two tangents to a circle through a point lying outside the circle. P is a point which is lying outside the circle. So in the second case, when P is on the circle, the point is on the circle, we are able to draw the tangent? Yes. In the third case, where P is outside the circle, the point P is outside the circle, are we able to draw the tangents? Yes, that too we are able to draw two different tangents. Now there is a property of these two tangents, that the length of these two tangents are always equal. So suppose if this is 6 centimeter, this will also be 6 centimeter. And the length of the segment of the tangent from the external point P and the point of contact with the circle is called the length of the tangent. That means if I were to name this T2 and T1, so here they are saying P to T1 or P to T2 are known as the length of the tangent. Now, with the help of a theorem, we are going to prove that the lengths of the tangent taken from an external point to a circle are equal. So, let us begin with our theorem 10.2. Theorem 10.2. It says the lengths of a tangent drawn from an external point to a circle are equal. The same diagram we are going to write over here. Now, let us see whether the lengths of the tangents are equal or not. So first let us draw a diagram. This is a circle, alright. From here, I am drawing two tangents here. Say suppose this is the point. Let me see if I am able to do justice to this drawing. So here is the point P, and I think it will go a little bit lower. I think we are almost there. Yeah. So this is the tangent. If you all can imagine the tangent here. I will shift this circle in a big, yeah. So here is the diagram. Okay. Let us label this as point A. This as point A. Then this as point P. The center as O. This point as Q. And these are the tangents. Okay. So we have to prove that the lengths of two tangents drawn from an external point to a circle are equal. So first of all, we will write what is given to us. Given is AP and AQ are two tangents. Are two tangents from a point A from a point A to a circle C O R. Okay, O is the radius. We have to prove. So to prove, what do we have to prove? To prove that AP is equals to PQ. The length of the tangents are equal. So we have to prove that AP is equals to AQ. Sorry, this is going to be AQ. Please write down this much, children. Now, one construction we are going to do that also you are going to write. One construction that join OP, OQ and OA. Okay, so we have to join OP from the radius. This we have to join, then OQ and OA. Okay, so this is your diagram. Copy down this much, children. Then let us come to the proof part. So here is the proof. In order to prove that AP is equal to AQ, we will first prove that triangle OPA is congruent to triangle OQA. Here we are going to bring in the congruency. Okay. Now we know since a tangent at any point of a circle is perpendicular to the radius through the point of contact. We know this particular property. We know that we will write, we know, make this to an implied sign. We know OP is perpendicular to AP and OQ is perpendicular to AQ, right? If you see the diagram over here, you will understand in a better manner. OP, this particular line, is perpendicular to AP. Okay, AP, sorry. And OQ is perpendicular to AQ. The shortest distance is the perpendicular, and with the theorem also we have proved. So with this, what do we comprehend from this particular property? That angle OPA and angle OQA both are 90 degrees. Since they are perpendicular, so the angles will be same. Okay. Let this be equation 1. Now, in triangles OPA and OQA, we have the first thing we have is that OP is equals to OQ. Why OP is equals to OQ? Radii of the circle are always equal. So you are going to write radii of the circle, right? Then we also prove that the angles are equal. Angle OPA is equals to angle OQA, which is equals to 90 degree, right? And one side is common, that is OA, and OA is equals to OA. So in bracket you will write common. So two sides are equal and one angle is 90 degree. So by RHS criterion, of congruency or of congruence, we get triangle OPA is congruent to triangle OQA, which implies what? Which implies AP is equals to AQ. Hence proved. Okay, so this completes your theorem, children. What did we do? We just did a small construction. If you see, understand from the diagram, we know from theorem 10.1 that the over here the radius on the tangent with the point of contact is, they are always perpendicular. The lines are always perpendicular, isn't it? The tangent at any point of a circle is perpendicular to the radius through the point of contact, right? And we did one small construction. We constructed, or we joined O to Q, O to A and O to P. And we had taken two triangles, that is APO and AQO, and we proved them by RHS congruency that they are congruent. Therefore, AP and AQ are equal. I hope you all have understood this, children. Please copy it down. Let's start with question number 1 of exercise 10.2. From a point Q, the length of the tangent to a circle is 24 centimeter. So there's a point Q and the length of the tangent to the circle is 24 centimeter and the distance of Q from the center is 25 centimeter. So let us draw the diagram first of all. This is the circle. This is the point O. Clearly the point Q is somewhere outside the circle, right? So let this be point Q. They are saying from a point Q the length of the tangent is 24 centimeter. Okay. Suppose I draw the tangent like this of say 24 centimeter. Let this be P. So QP will be 24 centimeter. And the distance from Q to the center, that is, center is the O, right? Till here the measurement is 25 centimeter. So what will be the radius of the circle? To find out the radius of the circle, what we are going to do from O to P by using theorem 1.10.1, we are going to join this line. And once this line is joined, this becomes 90 degree. So we have the 25 centimeter. If this is 90 degree, this is the hypotenuse, this is the base, and this is the side that we have to find. So from the figure, by using hypotenuse theorem, we're going to write OQ square is equals to OP square plus PQ square. OQ square is 25 square is equals to OP square. We don't know. PQ square is 24 square. This gives us 625, which is equals to OP square, plus this gives us 576. So bring 576 to LHS, we get 625 minus 576, which is equals to 49, which is OP square. So 49 square root is equals to OP. We get the answer as OP as 7 centimeter. So therefore option A is correct. Which option is correct, children? Option A is correct. That is, the length of the radius or OP is 7 centimeter. Copy this down, then we will move on to question number 2. If TP and TQ are the two tangents to a circle with center O so that angle POQ is 110 degree, then angle PTQ is equal to how much? Alright, so let us draw the diagram first of all. This is the diagram. Let me bring this little bit here. Yeah. So this is O. This is Q. This is P. This is P. And from here we have T. This is 110 degree. Okay. This line will be joined from here, children. Just draw the diagram correctly. So, how to prove it? We know that in the solution part we can write that angle OPT, okay, angle OPT is equals to 90 degree. We know that these are the right angles, right? These are the right angles. And angle OQT is also equal to 90 degree. And angle POQ is equals to 110 degree. So how do you determine this? If you see this particular shape, it is forming a quadrilateral, and all the internal angles, the summation of all the internal angles of a quadrilateral is equal to how much? It is equal to 360 degree, right? So from here, we are going to add up all the angles to find out the fourth one. So from here we will write it as angle. We will write first, since POTQ is a quadrilateral, we know angle POQ plus angle OPT plus angle OQT plus angle PTQ is equals to 360 degree, right? So from here we get the answer. Angle POQ is 110 degree plus 90 degree plus 90 degree plus angle PTQ is equals to 360 degree. 110 degree plus 90 is 180 degree plus angle PTQ is equals to 360 degree. So this on addition gives us 290 degree, right? So 360 degree minus 290 degree. How much do we get? 9 and 16, 10, 11, 12, 13, 14, 15, 16, 70 degree. So your answer is 70 degree, that is D. Option D is correct, 70 degree. Is that clear? Very simple. So with this, question number 3 is your homework. Okay, children? Question number 3, I know you will be able to do it. This is your homework. Let us move on to question number 4. Okay. Question number 4. Prove that the tangents drawn at the ends of a diameter of a circle are parallel. So for this, let us see first of all the diagram what they are trying to depict. We have to draw the tangents at the ends of a diameter of a circle. Okay, and we have to prove that they are parallel. So this is the circle, and let this be the diameter. Let this be O. and let this line, let this particular line be A and B, and the tangents drawn at the end of the diameter. So these are the two ends. These are the two ends. Okay, and these are the tangents. So these are the tangents. Let this be P and let this be Q. We have to prove that these lines are parallel. That means line P is parallel to line Q. Okay. So first of all, we are going to write what is given. We have that AB is the diameter. AB is the diameter that is given. P and Q are two tangents. P and Q are two tangents that is also given. What do we have to prove? To prove that P is parallel to Q. Okay, we have to prove that P is parallel to Q. Now, we know in the proof part we will write, in the proof part we are going to write that since they are tangents, P and Q are tangents, since P and Q are two tangents, therefore OA is perpendicular to P. Okay, this particular line OA is perpendicular to P by theorem 10.1, and OB is perpendicular to Q. This particular line OB is perpendicular to Q, right? So over here we can name this as let us take this particular angle. Okay, both are 90-degree, no? So any of the angles we can take. I'm taking this particular angle. So over here let this be angle 1 and let this be angle 2. Okay. Now if you see angle 1 and angle 2, we know angle 1 and angle 2 are what? They are equal, right? They are both 90-degree. Also they are alternate angles, isn't it? They are alternate angles. So we can say since angle 1 is equals to angle 2, which is equals to 90-degree, also angle 1 and angle 2 are, they are alternate angles which are equal, right? This is one of the property for the parallel lines, isn't it? So since these two are alternate angles which are equal, therefore line P is parallel to line Q, hence proved. Okay, hence proved. Easy enough. That OA is perpendicular to P and OB is perpendicular to Q. Also, through alternate angles, we are saying, now these are the tangents. So, we know that they are 90-degree, isn't it? This angle is also 90-degree, this also. Angle 2 is also 90-degree, this angle is also 90-degree. So, to bring out the property of the parallel lines, I have taken the alternate angles which are equal to be 90-degree, and therefore the lines are parallel. That means the lines P and Q are parallel. Question number 5 is your homework, children. Let us move on to question number 6. Question number 6 is saying the length of a tangent from a point A at a distance 5 cm from the center of the circle is 4 cm. Find the radius of the circle. So first of all we need to draw the diagram. Let us draw the diagram for this particular question. This is a circle. This is O. Let this be O. The length of a tangent from a point A at a distance. So A is lying outside and A is a tangent. So let this be the tangent. Let this be the tangent. Say P. Let this be A. And the length of a tangent from a point A at a distance is 5 cm. From the center of the circle is 4 cm. Okay. So this is the particular line. Let us join OP. So here this is 5 cm and this is 4 centimeter, right? In the question they are saying the length of a tangent from a point A at a distance 5 centimeter from the center. So from the center it is at 5 centimeter and the length of the tangent from the point is 4 centimeter. We have to find the radius of the circle, that is OP. Now we know by theorem 10.1 that the radius at the point of contact when it is touching, it forms 90 degree, isn't it? So over here we will write, we know OP is the radius, OA is given as 5 centimeter, AP is given as 4 centimeter, right? And angle OPA is equals to 90 degree. The reason being radius and tangent, are perpendicular. Okay, so these are the given part. Now let us come to the solution of this. By Pythagoras theorem, we will write by Pythagoras theorem, we will write over here OA square is equals to AP square plus OP square. So here we have 5 square is equals to 4 square plus OP square. 5 square is 25 is equals to 16 plus OP square, which implies 25 minus 16 is equals to OP square. So what do we get from here? We get 9 is equals to OP square. Under root of 9 is equals to OP, which gives us the radius. Sorry, this is OP, which gives us the radius 3 centimeter is equals to OP, which is the radius. So this is your answer. 3 centimeter is your answer. I hope this is clear, children. We will end our class here. In the next video or during the live class, I will let you know more about exercise 10.2. We will continue from question number 7 to the last question. Thank you, children. God bless you.